Yeah, you are audible. At least once I could hear that you said hello. Can you say it once again?
Hello.
Yeah, you are audible. Okay. Okay, so I think you can see my screen, right?
Yeah.
Right. So first is what is this Stokes theorem? So recently, sir has covered this Stokes theorem in his last one of the last lectures, and then what is its significance? I mean, why do we really use this? Do you remember the statement for the Stokes theorem?
Like using the Stokes theorem, we
Mm-hmm.
relate the line integral with
Mm-hmm.
the surface integral. It is like
Exactly.
an extension of the Green's theorem.
Very well. Yeah, you're right. Exactly. And do you remember how did we relate in the Green theorem? I mean, you can look at the notes also.
Like with the Green's theorem, we used like I had related it with ODEs. So we take a condition which resembles that of exactness of a solution. While
Yeah.
for Stokes theorem, we use the curl of the function which we are
Right.
trying to integrate.
Right. You're right. So, okay, suppose, okay, let me just write for the moment exact statement for the Stokes theorem and can we really apply it all the time? Hmm? So, solution. So, suppose we have some sigma to be any orientable surface and we are talking in R3 and suppose it has certain boundary, so whose boundary is a closed curve C and let our vector field be S P P I cap plus Q J cap plus R K cap. Of course, P Q R. These are functions of X Y Z. So I can write them as like P X Y Z and Q X Y Z like that. And this define. Okay, this is one of the important thing that I'm going to tell that this be a vector field defined on a subset of R3 that contains sigma. Then the line integral f dot dr or c is same as curl f dot ds or we sometimes write this as like curl f dot n then ds. This is vector, this is not vector. There is a difference. Sigma is that surface. Yeah, so are you able to follow this?
Yeah.
So I'm somehow focusing on one part here that contains sigma. That means you cannot talk about equality of this line integral and the surface integral unless your f is defined on this surface where you are talking about, where you want to integrate your f. You might remember that there was one example which Sir gave in his lectures that there was one point at which one of the vector field was not defined over one surface and somehow when he was trying to use this Stokes theorem he was getting two different answer. From here he was getting different and here different. That means it violates the Stokes theorem. Well, it actually do not violate because the assumptions are not hold. Unless those things are not true, you cannot even apply the Stokes theorem. Right. So, and as you said, the significance is once you want to compute the line integral, and sometimes you may not able to trace the curve over which you want to integrate, but surface is pretty fine if you are able to see the surface, and if you can compute the double integral, the surface integral, then it will be easy to compute the line integral, because there is a equality as long as your vector field is defined on the surface. All right, so that's all I want to say. So it is about relating a single integral with the double integral. So we can switch whenever we think that one of them is easier. Okay, now here is another question. We want to verify the Stokes theorem for this vector field with the surface is z equal to x square plus y square such that z is less than equals to 1. What kind of surface is that? Can you see that? If you don't see it, maybe on the xyz plane, if you can see in xy plane or xz plane, or either of the plane where
On
you
a 2D
can,
plane, it is like a circle.
it's a circle, okay, and this is when you are taking xy plane, right?
Yeah.
But if I take zx plane, because you have to analyze the surface in all planes, right?
Yeah.
So if you just if you just um what do I say, um suppose a certain figure is on 3D but you want to see in 2D, you just try to make the other variable to be 0. Suppose I want to see in the zx plane, you put y to be 0, then you will get z equal to x square. Similarly, if you want to drop x-axis, put x equal to 0, you will be in yz plane where the equation is z equal to y square. So in those cases, what is the figure?
Parabola.
Yeah, it's a parabola, and this is why I think I should write here that this is nothing but so here the surface is a paraboloid. When you are working in 3D, you call it paraboloid. Okay, so let's just draw the figure for a moment. Mm, and can you see the direction as well? Suppose I put write this to be zx. I'm sorry. If I write this to be z axis, if I write this to be y axis, this to be x axis.
Z will always be positive.
Okay, so like how
So it will
do
be
I draw?
upward.
Yeah, right. So how do you see that? You just draw perpendicular to the zy plane, because zy plane you can see, and put x equal to 0, you'll get z equal to y square. So then you can realize z equal to y square is nothing but an upward parabola. So yeah, see that this is somewhat like this. And since the given z is at the most 1, so you're given that the height is at the most 1, right? All right, so yeah, starting from here. And suppose you want to see the, if you want to see the equation for this, just draw parallel to the y-axis, certain lines you can draw. And the first part it hits is this, the last part it hits, you can write the equation for this anyway. Okay, so yeah, we want to verify the Stokes theorem for this. So if we have to remember what is the Stokes theorem, then only we can verify it. So the Stokes theorem is about f dot dr over c, same as curl f dot n ds, and this is over the region. I should let me write the region to be sigma. Okay, I'll write this region to be sigma. So this is okay. So which part you think is easy to compute first?
The surface integral is easier.
Surface integral. Okay, let's compute the surface integral first. So okay, curl. So for that, you need to compute what is n cap. N cap, you remember what was that?
If it was phi u cross phi v divided by the norm of phi u cross phi v.
Yeah, so phi a was like a parameterization. Here we are not parameterizing because the surface is anyway given to be graph of certain function, right? I can write that as a graph of function. How? Because I can write this xy comma x square plus y square, right? Where my z is fx y, same as x square plus y square. So in this case, I don't actually need to parameterize. We can further need if there is, we want to simplify something, but it's given to be anyway a graph of a function. Okay, phi a cross phi b. This was n cap. In fact, it's unit normal. And since if you remember, we are all the time we are going in the which direction? It's anti-clockwise, right? So we are
So the
actually
surface should be to
running.
the left of our plane as per
Yeah.
the
So
convention.
suppose, yeah, suppose I'm moving on this circle, which I'm putting arrows over it. So your area, your part is in fact in the left of, right, the left of it. So we are going in the right direction. This is how this orientation is. Now let's compute curl f first. So remember f is zxy as coordinates. I will just write zxy. So can you tell me what is curl of f?
Curl of f is the cross product between the gradient of f and f.
Okay, this is what you are telling. See.
Yeah,
Okay, and we, if you remember, we can compute this by, okay, this is certain vector, this is certain vector. We know we can talk about cross product of two vectors. And what is this vector?
this is the gradient of f.
Yeah, so del by del xi cap plus del by del yj cap plus del by del z k cap. This is that vector, right? So I just simply put here del by del x, del by del y, del by del z. And f is nothing but z comma x comma y. So I'll simply zxy. What is this?
I'm gonna show the above part once.
Sure. Is everything okay?
Yeah, the curl will give us y minus x I cap plus z minus y j cap plus x minus z k cap.
Wait. Curl f is a vector and it is nothing but just the cross product. So how are you getting certain other thing? I'm a bit confused. Okay, what is this cross product? I mean, I have written this I
The
cap, J cap,
del
and
by del x will give us 1. Like the other two will also give us 1.
Just a moment. I think you're confusing something. We are computing this, right? Are you computing something else?
No, I'm computing this only.
Okay, you are computing this only. Then I cap I will just hold, and then I will leave this column and this row. What would I get? Del by del y of y minus del by del z of x, right? I
Okay.
think you are confused with something else.
Okay, now I got what is to be done.
Okay. So yeah, quickly compute and tell what is it.
So we get I cap plus j cap plus k cap.
Right. So it just, I think it will be, this is 1 and this is 0. So it is just I cap. And similarly, you have to do j and k all. So I'll just write. Yeah. So our curl f can be checked that it is just I cap plus j cap plus k cap. Right. So we got a vector. Now we want to find, just by the equality, I have to compute curl f dot n. So at least I have to see what is n in this case. So we do not have any parameterization. In this case, my r is nothing but r of x, y, z, and my z is just x square plus y square, right? We do not have any parameterization. So when we have parameterization, if you remember, we do phi u cross phi v and then phi u cross phi v, where u and the parameterized variables u and v. Here the variables are x and y. So it is simply rx cross ry and then rx cross ry norm. Is that okay?
Yeah.
Okay, so can you compute this? Today's tutorial will be completely based on computations. Okay, let's compute it together. Okay, we want cross product. I should be it should be Rx ry I cap j cap k cap. Yeah, so Rx meaning I have to take the partial derivative of this vector. Vector meaning I have xi cap yj cap plus x square plus y square k cap. This is my position vector. If I want to find any position on the surface, this is how I have to find, right?
Yeah.
So Rx meaning I have to just take the partial derivative of this vector. So what That would be
102x
102x, right?
and
And
0,
now
1,
what is
2y.
Ry? Yeah, 0y, 2y. So I just have to compute this, which is nothing but,
Minus 2x
yeah.
minus j into 2y
Mm-hmm.
plus k cap into 1.
Yeah, right. So we got this cross product, but in order to compute the unit normal vector, I should be dividing this by the norm. So what is the norm?
2 square plus 2 square plus 1 whole under root.
Yeah, it is 1 plus 4x square plus 4y square plus 1. Well, there can be any other ways also. If you remember, to any surface, if we want to compute the unit normal, then gradient of f is the one which is normal to the surface. You remember that?
Yeah.
So you can compute this by that also. It is same thing, just the same thing. All right. So we got this unit normal vector. Let's just now compute curl f dot n and then ds. And this is over the surface sigma. Now, if you remember, there is a way to go from ds to dx dy. Yeah, we always compute dx dy. We always try to compute this something with the function depending on x, y, and here is the limit for x, here is the limit for y. But ds is the small surface area. However, dx dy is the area. So, how to relate? I think we discussed this part, how to change ds to dx dy. Yeah, one has to make some changes. It's not direct, like you have to change something. So let me just try to show you that this is nothing but if you have RD of RUV, then this is nothing but, sorry, this is nothing but RU cross RV norm times DUDV. Do you remember this? Suppose we have a
Yeah.
parameterization. Yeah, if we have certain parameterization, this is what we do. But in this case, how things will change? Yeah, can you tell me in this case when we do not have any parameterization, how do I write this? Just follow up what we did above. Whatever we did above is going to help you.
We will take the cross product between norm of the cross product between r x and r y.
Yeah, so we do not have UV, but we have dependent variables x and y, so everything will be in terms of x and y. So it will be curl f dot n, and then we have rx cross ry times dx dy. Yeah, this is how we compute the small surface area, and this is over the region over x and y. I will just take D as the domain. Okay, I will just write D to be the domain over which we are varying my x and y. Okay. So this is surface and this is something else. Okay. So yeah. Let me just write everything now. Curl f, we had I plus j plus k cap. So what is the dot product with the n cap? So dot product,
That
I'll
is
just write minus 2x minus 2y plus 1 by 1 plus 4x square plus 4y square times norm. Anyway we have computed norm of rx cross ry is nothing but 1 plus 4x square plus 4y square, isn't it?
yeah.
And then we have dx dy. Now one has to be careful about looking at the limits. So I'll simply write d for the moment. I will just cancel whatever is being cancelled here. So yeah, so what we are left is integral minus 2x minus 2y plus 1 dx dy over the region D. Okay, so let's go back to the question and then let's look at the limits for x and y. Can you see limits for this? If you just you know mm, if you just make everything perpendicular to the xy plane, what would you get? If you take z to be 0, you'll get x square plus y square equal to 0. If you take z equal to
Yeah.
half, you'll get x square plus y square is half. If you get z equal to 1, then you get x square plus y square equal to 1. So from where to where the limits are varying for x and y? Hmm?
Okay, just a minute. Okay, if
Mhm.
x can be varied from uh, just
Okay. Maybe try to simplify. You take z equal to 1. That means you are getting circles of radius up to 0 to 1. Yeah. So
yeah.
each time you're getting circles varying their radius from 0 to 1. And since you are completing each circle, so the angle is theta from 0 to 2 pi.
2 pi.
Yeah, so in this case, we are getting circles. So I will just basically, if you try to see from here also, the equation, if you try to if you try to pull this graph to the xy plane, you will get circles, and then it is all about you are getting this kind of thing, right? And this is from radius from 0 to 1. Yeah, you're getting concentric circles from 0 to 1. So equation, if you want to see equation, it is like minus of it's you have to separate in the upper hemisphere and the lower hemisphere. They both have different equations. So you have to go from minus 1 minus x square to 1 minus x square if you are writing radius 1. Yeah, so you
Yeah.
should be able to write like this: minus of a minus x square, or a square up to a square minus x square. And from a you have a limit. A has to go from 0 to 1. Yeah, like that you have to do. So I will just simply say the easier way is to go to polar coordinates. Yeah,
Yeah.
you
Yeah.
because you may not miss anything then. So what do I do? I just write x to be r cos theta and then y to be r sin theta. My theta, since I'm covering complete circle, so it is from 0 to 2 pi, and r is, for me, it's a variable now. Yeah, r is not fixed to me. We are varying r from 0 to 1. So then dx dy, how would that change?
R T R D theta.
Yeah, so if you remember, it is r d r d theta. It's like change of variable things. So then I will be just now computing r from 0 to 1, theta from 0 to 2 pi, and then this is minus 2r cos theta, minus 2r sin theta, plus 1, and then r dr d theta. Yeah. So can we do this? I think we can.
Yeah.
So yeah, quickly try if you can. Just integrate first with r. Okay, let's just,
2
yeah.
pi gives us the same value as 0 degree, right?
For,
For trigonometric functions.
it depends, right? If you have sine function, sine starts from 0, it is at 2 pi, it is 0, but if I take cos, it will be 1 at 2 pi. This is cos, this is sine. It depends what function you are dealing. Okay, let's just do it.
So like cos at 0 is also 1, at 2 pi also it comes back one cycle.
Right, so
So the okay answer is 2 pi.
okay, let's just do it. Minus 2r square cos theta minus 2r square sine theta plus r, and then I just shift the graph. T r d theta, and then this is from 0 to 1, 0 to 2 pi. Yeah, for me theta is constant for the moment, so I'll just integrate with respect to r minus 2r cube. Is that okay? Square by 2, 0 to 1, d theta, 0 to 2. Yeah. Minus 2 by 3 cos theta minus 2 by 3 sine theta, and then 1 by 2. That's all. Are you getting the same?
Ma'am, show a little above once.
I just multiplied r 3 component. Did you mix up something?
Yeah, I did. One at one place.
Okay, yeah, you have to be careful while computing things. Okay, just multiply throughout r and then keep theta constant, integrate with respect to r. This is how you would get, and then cos, its integration is sine.
The answer would be only pi.
Okay, let's just see. 2 by 3 cos theta, and then theta by 2, and then from 0 to 2 pi. Okay, sine 2 pi, sine 0, both are 0. Cos 2 pi is 1, and cos 0 is also 1. So this is going to be 0, this is going to be 0. So it is only 2 pi by 2, which is pi. Yeah, answer is pi.
This could be a trick, maybe. Like whenever a trigonometric function goes one whole cycle, it comes back to the same value.
Ah, okay, okay. This is what you are pointing out, right?
Yeah. So
Correct, correct.
those are default by default 0.
Correct, correct. So yeah, it's like their periods are coming, and so you are computing at the same period. I mean, at the same values, so therefore they are 0. Yeah, right. Right. So what we did till now, we were okay. Let's go back to the question. We were trying to verify the Stokes theorem, and what we got is that curl f dot n, which you were thinking to be simple enough, it took some time to compute, and we got the answer to be pi. Let's just compute the line integral. I think that is simpler. Why? Because it is just the circle, right? Each time you are moving on a circle, the surface of this paraboloid is nothing but it's a circle, right? If you see at the top, your each of them, I mean, the region that you are somehow taking the curve is nothing but a circle, and you are parametrizing a circle. That's all. So the line integral over the curve is nothing but a circle. So I'll just write. Let me just write what we are trying to compute. We are trying to compute f dot dr over the curve C, and C for me is a circle. And it can be parameterized. So if you see carefully from here, it is nothing but the circle is nothing but the radius one circle, and you are moving anti-clockwise direction. So if you want to parameterize it, how would you parameterize it? Z is anyway 1, x is you can take to be cos theta, y you can take to be sine theta, and theta varies from 0 to 2 pi, isn't it?
Yeah.
So I think it is a bit simpler in this case. So if you remember, f is nothing but x I cap. Oh, I don't remember. I have to see. Z I cap x y x j cap x j cap and then y k cap. Okay, so by definition, this is z time dx, because to me dr is nothing but dx I cap dy j cap plus dz k cap. Yeah. So dot product is z dx plus x dy plus y dz. And I have to parameterize the curve, which I have parameterized by x is sine t, sorry, y is sine t, and t varies from 0 to 2 pi, and z is 1. So then there is no dz if we, sorry, what did I do? Did I do something wrong?
R cos t or sin t. But R is
Just
1.
a moment.
No, R is not 1.
Yeah, R for me is 1. R is okay. No, I think we are doing right. Yeah, we are doing fine. Yeah. So t is, for me, the variable is t. T is 2 from 0 to 2 pi. Z is 1. Time dx is minus sine t. Then dx is dt. Plus x is cos t. And then y is cos t dt. And there is no dz. Is that okay? Yeah, dz is 0. Z is a constant function. Is everything okay?
Just a minute.
Z is 1, and then dx is nothing but minus sine t dt. X is cos t times dy. Dy is cos t dt. So I have written that part. And plus y dz, but z is constant, therefore dz has to be 0.
Yeah.
So it is 0 to 2 pi, and then cos square t minus sine t, then dt. This is all. Is that fine? Let's just go back what we did. F dot dr by definition is z dx plus x dy plus y dz. I want to just parameterize the curve. So what curve we are moving? We are moving on the plane z equal to 1, which is being, the boundary is nothing but the unit circle. So I just wrote x to be cos t, y to be sin t, t from 0 to 2 pi. But since we are moving on the curve z equal to 1, so z is 1, so it's constant, dz has to be 0. Everything is okay, right?
Yeah.
So can you integrate this?
Yeah.
Square t. Okay, let's just do it together. 1 plus cos 2t by 2. This is what we use. And minus sine t, and then dt, and then 0 to 2 pi. So as you saw, trigonometric functions over 0 to 2 pi, they are going to be 0. So I'll just simply put them 0. 1 by 2 times dt, 0 to 2 pi. This is nothing but t by 2 from 0 to 2 pi, which is pi. Is that
Yeah.
okay?
Yeah.
So thus we verified the Stokes theorem. We really did. And in this case, the line integral was simple, right? Although, I mean, both were simple, but it was taking certain time, the curl f dot nds. So we simplified and we verified that Stokes theorem is valid. Okay, here is another question. Suppose we have a elliptic paraboloid. You understand elliptic paraboloid?
Yeah.
Yeah. So we have this figure. We have this surface, and again, this is we don't need to parameterize. It's a graph of function. Yeah, we have x, y, and then z is given in terms of x and y. So and C be its boundary curve. If I ask you what is the boundary for this, hey, you are going at the top. So boundary will be at the top part, right?
It will be the
Uh,
ellipse x
yeah.
squared
So
by 2 square plus y squared by 3 square equals to 1.
equals to 1. Yeah, exactly right. So z equal to 1 is going to give you the boundary, and then that you'll get your ellipse. This is why you are calling it as elliptic paraboloid. And one way question is to compute the line integral. Again, now it should come to your mind. What do you want to compute? You have this vector field given to you. C is given to you, the boundary curve for this elliptic paraboloid. What do you want to compute? If you want to compute this line integral, how would you proceed? Would you really go for the line integral, or you would do something else? I mean, can you use certain result in order to simplify your computations?
Just I'll think about it once.
Mm-hmm.
We have to parameterize the boundary curve first.
Right. Let's just write for a moment. So C is nothing but it is all those points x and y such that x square plus 4 by y square by 9 equals 1. Yeah, this is what our curve is. And we want to parameterize it. So how do you parameterize? Simply just use the idea of parameterizing a circle.
A polar coordinates
Right. So how do you write it? X equals to?
r cos theta, but
Okay,
r
here
is
is
1 for our.
just a moment. When you have circle, you have x. There is no x square by a square, right? A square for you by default is 1.
Yeah.
Here you have to be a bit smart in order to write this coordinates. What do you choose your x such that x square plus y square by 4 by 9, same thing like x square by 4 plus y square by 9, that turns out to be 1. You know that x has to be chosen in terms of cos, right? Let me just write for the moment. If you have ellipse, then you are writing 2 and then 3. It's something like this. Not drawing it perfectly, but something like this. Yeah. This is what our ellipsis has. This is part is 2 and this part is 3. There is no r, so that you can write x to be r cos theta, but you can wisely choose that in place of r, what do you choose? Such that when you write x
A
square
cos
by
theta.
4, sorry,
A cos theta.
okay, okay, and what is a in this case? You're right.
A is 2.
Exactly. So you choose a to be 2. And what about y? Y equals to?
B sin theta.
Exactly. Now what would you do? If you write x square, it will be 4 cos square. 4 get cancel, you'll get cos square. Y square, you'll write 9 sine square. 9 will get cancel, you'll get sine square. And cos square plus sine square is 1, right? So yeah, you have chosen x equal to a cos theta, y is b sine theta, a and b are these. So we have parameterized it. And z is anyway, the surface over that is nothing but, sorry. And of course, z is 1 is the constant thing that you have to carry. So z equals to 1 is the thing. One thing what you can directly do is 9xz, I'm just writing f over what is written, 9xz plus 2y and dx plus 2x plus y square dy plus minus 2y square plus 2z is dz, and over the curve C which we have written. So clearly this part goes away because your z is constant. Is that okay? Hello?
Okay, how does that go away?
Sorry, which thing
Like
do you want me to?
like
Sorry.
2z, you said it becomes 0 because it's a constant.
No, not 2z. I'm writing dz. This goes to 0 because z is 1 in our
Yeah, yeah.
curve, right? So dz becomes 0. So the whole part basically goes to 0. This is what I want to say. Okay, one thing is that you directly put your x and z and find what is dx and then multiply and then solve it. You can do this, right? You know what is x, what is z, what is y, what is dx, and how to integrate. So your integration will be 0 to 2 pi and everything will be in terms of theta and finally d theta. Is that fine?
Yeah.
I would leave this to you. What I want to say here,
You
sometime we
can
can
try
switch.
Green's theorem.
Yeah, so let's use Stokes theorem then. So this is one way which we did. So we know how to compute the line integral without any help, but let's just do it with the help of Stokes theorem. So using Stokes theorem, we have f dot dr over the curve C is curl f dot n ds, and this is over the surface sigma. I'll write the surface to be sigma. S is given to us. S. Do not confuse with this. Maybe I'll write sigma and sigma. Okay, so what is curl f? Let's just compute that. F is given to you. Can you compute curl f? Let me just copy the f. Yeah, this is our f. So curl f will be gradient, sorry, cross product with f. So it is I cap, j cap, k cap, del by del x, del by del y, del z. And f is to me and 9x plus, sorry, 9xz plus 2y. Y is 2x plus y square, z is minus 2y square plus 2z. If we find this, this would be I cap minus 4y minus 0 minus j cap 0 minus 9x plus k cap 2 minus 2. Is that okay?
Yeah.
Okay, so we'll get minus 4y I cap plus 9x j cap. That's all. We do not have k cap. I'll just write 0 dot k cap, right? So this is what we got as curl f. Now what is n? If we remember, it was rx cross ry because I don't need to parameterize the surface. Rx cross ry. No. R, you remember you have to take care z. Yeah. So your R, any position vector, is nothing but R of x comma y comma x square by 4 plus y square by 9. This is your z. So what is your Rx?
1 0 x by 2.
Right. So I'll just write I cap j cap 1 0 x by 2 is that okay? Yeah. And we had x comma y comma x square plus This was our position vector. So what is ry? Is it fine? So what we get is minus x by 2 I cap minus 2y by 9 j cap plus k cap. Is that okay? Yeah. This is fine. So this is
Yeah.
our cross product Rx cross Ry, and then we have to compute n cap by writing x square by 4 plus 4y square by 9 plus 1. Fine. Okay, let's just compute curl f dot n. This is the first thing we have to do. You have curl, you have n. Can you do the dot product?
Minus 2xy 0.
Is it 0?
Yeah.
Yeah, so you're right. So curl f dot n comes out to be 0. I'll just leave this part. This is 0. And therefore, what is your integration?
Mm,
You can
It
write it
becomes
directly.
0.
Yeah, it becomes 0. So earlier you had to do so many things in order to get 0, but now simply curl of that dot n will tell you the answer is going to be 0. Okay, I think it's a simple thing. Okay, let's just do one more question. Verify Stokes theorem for the vector field S, the surface bounded by again a paraboloid and the plane z equal to 0. How the paraboloid look like? Whenever such thing comes, one should be
We put
um,
something equal to 0.
yeah. Look, this graph in all planes and
It starts at z equal to 4.
okay, so that you got that z equal to 4 is the starting point. Let me just draw in. We keep this x, this y, and this z. Z we always considered as a height. Okay? So when we have x and y both are 0, we got z equal to 4. So something here we have to start. It's written it is paraboloid. So how would you go? Would you go this way or would you go this way?
It will go lower
Because
like because when x and y are increasing from 0,
uh-huh.
value of z is decreasing. That means the circles open below z equal to 4.
Okay, this is one way to see. Another way.
And after that, it is bounded by the plane z equal to 0.
Okay, so you basically understood by the statement itself. Yeah. One way is to be smart enough to understand the statement which says it is a bounded region between z and 0 and something if you go above it will not be bounded. So yeah, another way is to just I'm just forgetting that word. What do I say?
Okay, like
Project.
x
Yeah.
square and y square, they are
Mm-hmm.
by themselves positive anyway.
Mm-hmm.
So
Mm-hmm.
when we put a negative sign in front of them, they will
Mm-hmm.
be negative in total. So they will,
Okay.
as a result, reduce the value of z as they increase.
Right. Yeah, you're right. Yeah, correct, correct. Yeah, so you're right. Another way is You just project this surface to the planes, various planes, as I told you. Project this to ZY plane. X is 0. You'll get. Just a moment. Is there anybody who's waiting? Just looking. Looks like something is happening. Yeah. Hello? I have to see who has just joined. Steffi, can you hear me? Hello? I don't think he is. Okay, so let's just continue. I think you joined very late. I'm not sure how would you catch up the things, but let's just continue. Yeah, so we have this. So just project this surface to z y plane, and then you will get z equal to 4 minus y square. And then you know that how to draw the graph in 2D. Z equal to 4 minus y square. Yeah, it is the downward parabola, isn't it?
Yeah.
So you can get it by that, and it will be like this. But it can go beyond, right? It can keep going like till the infinity. But since the point is that it is bounded by the z equals to 0, that means you are in the xy plane, and then you have to stop. So I have to stop, and then I will just simply draw. Yeah. This is how we will get this z equal to 4 minus x square minus y square. Now what do? We have to verify Stokes theorem. So the curve is this, right? You are finally over this curve, and you have to parameterize in counterclockwise because you always want to be in the left of your surface. So yeah, this is how you have to parameterize. And finally, what is the equation? If you just project the surface to the xy plane, at the xy plane, what it would become? Can you tell me that?
X square plus y square equal to 4.
4. It's a circle. So therefore, it needs to be visualized that this is actually a circle of radius 2. Of course, I'm not drawing in perfectly because it's in this xy plane. The way I'm drawing, it's like looks like zy plane, but it should be an xy plane. So finally, the curve you have to parameterize is a circle of radius 4. Is that fine? Is that okay?
Yeah.
All right. So yeah, let's just compute first line integral. So Stokes theorem says you can relate line integral with the surface integral. Yeah, so f to me is given to me, dr is that. So let me just write that for the moment. Z minus y times dx plus z times dy minus of x plus y times dz. This is f dot dr, yeah? And the curve is nothing but this c. This is my c. And can you parameterize this? I think you can.
Yeah.
Okay, so c is nothing but it is all those x pi such that x square plus y square equals to 4. And note that we want to make sure what is z. Z is 0 to us. Okay, so what do you write? Tell me, what do you do now? I think it's just left to parameterize, right?
Yeah.
Okay, so tell me, what do you do now? Okay, just do it together. I think you are not responding. Z equal to 0. Okay, let's just put for the moment z equal to 0 in the beginning itself. So will be just y minus y times dx plus x times dy. This is what we have to compute over the curve. But the parameterization of x and y is, I'll just parameterize x to be 2 cos theta, y is 2 sin theta, and theta goes from 0 to 2 pi. Isn't it? We get x square plus y square equals 4. X is r cos theta, r is 2. So is it fine?
Yeah.
Why why you are taking so long like to do this?
Okay, I was thinking something else, I think.
Mm-hmm.
That simple
Okay.
things go out of
Yeah,
our mind
yeah.
sometimes, and we start thinking more complicatedly.
True, that happens. I agree. When we get into so deep, then we just leave the surface sometime. Right. Okay. So 0 to 2 pi, y is minus 2 sine theta, dx is minus 2 sine theta d theta, plus x is 2 cos theta, and dy is 2 cos theta d theta. Is this okay?
Yeah.
It is like 4 times sine square theta plus cos square theta. So what is the integration? 4 times cos square plus sine square, 0 to 2 pi.
It's,
Are you getting it? 8 pi?
wait just a minute.
It's just you can just simply go back and check. I think that person has left.
Now move to the next page.
Sure.
Like I'm getting 4 pi.
How that? Is that this is okay? Like 2 times. Okay, let's just do it. Minus y is minus time 2 sine theta, right? And then dx is again minus 2 times sine theta d theta. You might have missed 2 here.
Okay, wait. I missed the one thing.
Sorry, what did you miss? I think this is how helping you here. If we are doing these computations, that whether you are thinking correct or whether you are doing it correct or not.
Just a minute. Okay, now I got it. How it's coming 8 pi. Okay, like
Mm-hmm.
like we can also write sine square theta as 1 minus cos 2 theta by 2.
Oh my God!
But
I were.
instead of that, I wrote it as 2 sine theta cos theta and directly made it 0 from that
Oh,
trick which we just found.
okay. I mean, sometimes simple things you make a mess out of it. Anyway, so yeah, if from the line integral we got this, but we need to verify Stokes theorem. Now this time you have to be careful in your calculations and tell
Okay,
me
I
what is.
I just noticed what I missed. That
Okay.
sine square theta plus cos square theta is 1. But I was
You
going
missed this
somewhere
part.
else.
Oh my God. Anyway, this is why I was wondering. I mean, this was so simple, and why are you taking so long to do this? Okay, good that you got your mistake. Um, let's just verify the Stokes theorem. So we need to find the curl f, and then we have to find the n, and we have to take the dot product. And then this time you have to be careful and tell me what is curl f correctly. Okay, meanwhile I'll just copy my f so that I can write on the next page. Okay, what is that? Okay, when we try to take del by del x of this function, it will be 1 minus, and we take del by del y of this function, it will be again minus 1. Is that okay?
You took the wrong combination.
Sorry. Oh. Yeah. This time you are careful. I cap. Yeah. So del by del y of this is minus 1. And then z of this is minus 1 again. Then minus j cap. Now the combination is the first and the last one. So del by del x of minus of x plus y is minus 1. And then del by del z of z minus y is plus 1. Oh, but there is a minus over there. Yeah. Plus k cap. And then this time this is the right combination. It is 1 and then minus of minus 1.
Okay, with I cap it would be a +1.
Sorry,
Like we get a -1, but there's a minus already outside.
no, if I just take I
No,
cap time del by del y of minus of x plus y and then minus of del by del z of x plus z. What is this? This is what we have, right? So del by del y of this negative term is minus 1 and then minus of del by del z of x plus z will be minus 1 again. Is that okay? I think I'm careful.
uh, just a minute.
Okay, let me just point out here with the pointer. When you are doing this thing, then you have to take del by del y of this, which is minus 1, minus
Okay,
of,
I was taking the wrong combination this time.
you were only careful in the beginning and then you messed it up. Okay, minus 2i cap plus 2j cap and then plus 2k cap. So your curl f this. Is this okay?
Yeah.
Minus 2, 2, 2. You can write like this. Okay, we have this. We have to find n cap. N cap was Rx cross Ry, the norm of Rx cross Ry. So what is our surface? We have to find what is surface. Surface is 4 minus x square minus y square. So R to me is R of x comma y comma x square. So what was that? 4 minus
4
x
minus
square.
x square minus y square.
Yeah. So what is Rx cross Ry?
1 0 minus 2x.
Okay. Let me just see what you are getting. Sorry, what do you get? Let's just do
1
it
0 minus
carefully.
2x.
Okay, you are writing this first. Okay, what is Ry?
0 1 minus 2y.
Okay, let's just quickly compute this. It is minus 2y. Sorry, 2x. Let's just not do any mistake. Is that okay?
Yeah.
Okay, we got this, and just quickly do what is the norm, and then we know anyway. Whenever we have this ds, then the norm is going to get cancelled. You remember, this denominator and the ds part, they have norm. They will get cancelled. I just
Yeah.
need this part and curl f. That's all. I have to take the dot product of these two vectors. That's all. So use this vector and this vector and take the, so let me point out this and this, you have to take the dot product and then you have to do dx dy. Let's just do it quickly. Let me see what is this. Minus 2x minus 2. Okay, I'll write this way. Dot product with 2x 2y1 and dx dy over the region, let's say domain D. I have to find what is the domain. Okay, so just let me write minus 4x minus 4y plus 2 dx dy over the region. Now a disk D is, I think in this case is the disk, right? We have this z equal to this and then the plane z equal to 0. So the region between this is nothing but the, all the time we have squares, right? Sorry, circles. I'm doing this. We have this region x square plus y square less than equals to 4, right?
Yeah.
Equals to 4 is when we are in the xy plane, and if not, then we are basically um, going till z equal to 4, right? So in between we have z equal to 0 to z equal to 4. That means we have circles and the radius is going till 4. Okay. Yeah, so how would I rate this? How would I parameterize it? It's like circles from radius from 0
You
to
can move
2.
to polar coordinates.
Right. So how do you do that? How do you write that?
Like
You
x
will
equals
write
to 2
polar
cos theta.
coordinates for, yeah.
Okay.
So you'll write no. I mean you have to go less than equals to 4. That means you have to write from 0 to 4, right? In fact, you have to write till 0. A radius is 2 only. So you have to go from 0 radius to 2 radius and you have to take all the circles. That means you have two parameterization r and theta. R is varying from 0 to 2 and theta is varying from 0 to 2 pi. Is that okay?
Yeah.
I am a bit quick because I have to do some more computation, so I'll just write r from 0 to 2, theta from 0 to 2 pi, and write x to be, what do I write, r cos theta, y to be r sin theta, and dx dy would be r dr d theta. I would leave this to you and verify that is that 8 pi. Okay, I leave this. Let just, if we have time later, then we can come back. Okay, we have to write what is the Gauss divergence. Sometimes people call divergence only. What is the divergence theorem and what is its significance?
Are we getting 8 pi for the previous answer?
Are you getting?
Yeah.
Good. So it's verified then. So we have verified Stokes theorem. Very nice. So yeah, let's come to divergence now. Stokes has been gone, now divergence. So what is the Gauss divergence theorem? What does it say?
Like it relates the flux with a closed surface.
Mm-hmm. Okay, it relates flux over the closed surface to what?
Like we relate the volume integrals with that.
Right. So just like you did Stokes theorem, it tells you that you can relate the line integral with the surface integral. How this is related, it will gives you a relation between the surface integral and the volume integral. When we want to find the volume under the surface, then how do you do that? Do you need double integration, single integration, or triple integration? Hmm? What do you need? Do you need single, double, or triple?
Like if we represent the volume as just dx dy dz, then we need triple
Mhm.
integration.
Right.
Otherwise, double
So,
integration.
well, yeah, I mean, you can always change it to triple integration, even if it is not, but you can always change. So, yeah, triple integration is going to give you the volume, and you have to somehow relate that with the surface integral, which is always the double integration. Yeah. So let me just state it in a more precise way. Let me just state in more precise way. Mm, Give me a moment. I will just refer to certain book so that I will not just do any mistake. Yeah. So let we have S be any smooth. I will tell you later what is that surface in R3, and assume that S has some orientation outward. I mean, S is oriented outward, or sometimes people call counterclockwise. And let F be the vector field. And we always talk about vector field in this case, which has continuous partial derivatives. That means um, if I take del f by del x, del f by del y, or del f by del z, they should be continuous functions. Yeah, so the partial derivatives have to be continuous. This we assume on an open region where it happened on an open region, but it should contain that. Okay, that's a surface which that encloses a solid surface E in R3. I will give you the details what that mean. On an open region containing E, then integral over this E times divergence of F times dV. This is that F which I'm integrating, and this is the volume F dot ds for the surfaces. Oh, okay. So what does it say? I mean, you have certain surface, and whenever you want to find the volume, that means your surface. I mean, I should be able to find a volume under certain surface, right? Surface, I cannot find volume of a surface. Just like we have area is like it's the region below the curve you want to find. Same thing you want to find volume. That means it has to be region below certain surface. So below certain surface, and that solid region which is being enclosed in the space is what we call E, and surface to which we are saying that under that we want to find the volume is that surface S. And F is the vector field, that is okay. And if I want to find this, I mean the surface integral or the divergence or the volume integral, it makes sense over certain region containing E which has to be open. But anyway, let's just not go into the details. We just need to know the things over the region below the surface, and what is the region surface, what is the surface we have. These two things I want to relate. Does it make sense?
Yeah.
Okay, so this is what is the meaning of the divergence theorem, and here given F, how do you compute divergence F? Given, let's say, vector field, of course, this has to be, it cannot be a vector because I do not know how to compute the integral over the vector. It should be certain scalar function. Then only I know how to compute this. So it cannot be vector. So What does it mean then, divergence F? How do we compute?
It tells us about the nature of the vector field at a particular point.
Okay, this is what geometrically the meaning of divergence. Like just like you have F and you can talk about curl of that, it comes out to be a vector. Hmm? It's like cross product of with the gradient with the F.
Yeah.
Right? And what is the meaning here? What is divergence F? Okay, most natural thing. If I have to find a vector out of two vectors, you'll take the cross product. If I want to find a scalar from two vectors, what would you do?
Dot product.
That's all. So it is del dot F. For curl F, it was del cross F. For divergence, it is del dot F. And by definition, this is del by del x I cap, del by del y j cap, del by del z k cap times your F. Let's say F is F1 I cap, F2 j cap, F3 k cap. Then it would just be del F1 by del x plus del F2 by del y plus del F3 by del z, isn't it? And this is a scalar field. So now we can talk about the dV and we can talk about this equality. Makes sense. Okay, so I think we understood the meaning of this Gauss divergence theorem somehow, and let's just apply certain things. So we want to verify this divergence theorem. Does it really hold? We are given this vector field F. The surface consists of a cone. Cone is given to you, and but the point is here something important. The surface is not just cone, but we are including the circular top also. At the top of the cone, we have a circle. Can you tell me the top of the cone, which radius circle is that? At the top of the cone.
Radius 1.
Yeah. So at the top we have this one radius circle, and we want to take the surface. We want to include the surface by including the top of the cone also. Okay. Let's just verify this divergence theorem. Okay, well, let's just write once more. What is the definition? It is F dot NDS over the surface S is same as divergence F dot dV over the certain enclosed region E. An enclosed region is like because your region has been enclosed from z equal to 0 to z equal to 1. It has been enclosed. All right, so which thing will you think that this is be simpler and one can compute that simply? I think divergence.
Yeah.
I will go with divergence. Okay. What is divergence of F? You have to find that scalar field first. Definition is first component, second component, third component. Is that okay?
Yeah.
This is 1, 0, 1. The scalar only. 2. Simple enough. What do you want to compute here? If you want to compute the 2 times the volume, and this is volume of what? Can you tell me? I mean, just a moment. This is 2 times dV over E. Can you tell me what is this? This quantity. Isn't it volume of the cone?
Yeah, yeah.
Yeah. So, do you remember finding? Suppose you are given this cone, and then you are given this height, and you are given this R. What is the volume? There is a formula.
Yeah.
It will
The
be helpful
formula
if you.
is
Yeah.
1 by 3 pi r square h.
Good. You remember that? It's certainly good. 2 times 1 by 3 pi r square h. You have to now see what is r, what is h. Okay, can you tell me what is r and h from the given data?
R is 1,
And h is also,
1.
yeah. So in this case, h and r both are 1. So what is the answer?
2 by 3
2 by 3 pi.
pi.
Yeah, don't forget pi, r and h are 1. Good. So we got very easily, we got this divergence f dot dv volume. So yeah, let's just quickly compute f dot nds and we will try to equate whether they are equal or not. Remember, surface are two surfaces, this surface and this surface. Because if we look at the cone, this surface is something else, right? And this surface is something else. So you cannot combine, they have to be dealt separately. Okay, just do certain things. So we want to compute f dot n ds over the surface S1 I will write and S2 I will write. What is S1? S1 is the that region XYZ such that z square equal to x square plus y square and z is from 0 to 1. Yeah, and the other
Yeah.
region is that region where z is constant 1. There you have z is nothing but, sorry, am I confusing? Just a moment. Yeah, z is 1. On the top we have z equal to 1. So therefore we have just x square plus y square equals to 1. Yeah, we have these two regions. Is that okay?
Yeah.
For the first one, what do you do? Let's just write the formula very. Okay, what do you do here? You have this f dot nds. Just a moment. You will simply write f dot f of uv if you want to parameterize because it's a circle. And n, if you remember, and ds, if you remember, their denominator is going to cancel with the norm. So I will just simply write ru cross rv. Dot product
DUDV.
times dudv. Yeah, you're right. So hmm, for the first thing, I will parameterize just like this. We will write x to be r cos theta, y to be r sin theta, and then in place of z, I will have r. R will vary from 0 to 1, and theta is going to vary from 0 to 2 pi. Is that okay? So I will write this
Yeah.
part as r and theta comma z such that will we require theta? No, z, no. R and theta such that r square, r is from 0 to 1 and theta is from 0 to 2 pi. Of course, I mean, I'm writing x to be r cos theta, y to be r sin theta. Yeah, these two things one can relate. Yeah. So, yeah, just let's just compute what is this. F, let me write, let me copy. Yeah, this is our F. What we want to compute is RU cross RV. So R has been changed now to R of U. I will say this way. small r and theta, where r is from 0 to 1 and theta is from 0 to 2 pi. Of course, x is r cos theta, y is r sin theta, and z is r. If you have this coordinate, then you should be able to write what is r. I think I'm confusing, but one r is for r theta and one r is for the position r vector. I think but let's just, sorry, writing wrong. R cross r theta, I cap, j cap, k cap. So for if you differentiate your position vector x, y, z with respect to r, the first coordinate is x, which is r cos theta. With respect to r, it becomes cos theta. Y becomes sin theta, and then last is 1. And if I look at with respect to theta, then it will be minus r sin theta, r cos theta, and then 1. Sorry, 0. Is that okay? It will be
Yeah.
I cap is going to be r cos theta, and then minus j cap is going to be 1, I think, plus k cap is going to be, sorry, I think I missed something, minus r cos theta, minus j cap is r sin theta, and then k cap is r. Yeah, it looks now okay. Is it okay?
Yeah.
Okay, so let's just quickly put over there RU cross RV, R theta we have. Let's just write F dot with this cross product and this F, we have to take the dot product. Okay, so X is my R cos R, I'll take common, cos theta minus sin theta, I cap plus R times cos theta plus 1 J cap plus K cap R times 1 minus sin theta. This is my F, and then dot product with this the cross product of r and theta, which is minus r cos theta minus r sin theta, and then r. Okay, let's just quickly write this. It would be integration from r from, it's a double integration, r from 0 to 1, theta from 0 to 2 pi. And it will be minus r square theta plus r cos theta sin theta plus or minus r square cos theta sin theta minus r square sin theta plus r square minus r square sin theta. I think I might not be doing any mistake, but you can point out later. So minus r square cos theta and minus r square sin theta, they gave me minus r square, and that will get cancelled, I think. No. Yeah, it looks like that get cancelled. And what do we left is minus r square sin theta and minus r square cos theta sin theta and r cos theta sin theta. Okay, I am a bit confused now. You have to do this computation. I'll leave this for you. You have to do this, okay?
Okay.
And the same thing for S2. If you want to parameterize S2, then how would you parameterize? In this case, your r will be fixed because radius is 1. For S2, you will just simply write x to be cos theta, y to be sin theta, theta from 0 to 2 pi. And will that be okay?
Yeah.
All right. So r is from 0 to 1 and theta from 0 to 2 pi, and your z is fixed, which is 1. So you can do this. I'll leave this part. Okay, and you have to match up this value from there somehow. I mean, it's a bit lengthy. This question was a bit lengthy. I hope things are clear. You can do later, right?
Yeah.
Okay. Yeah, so I think how many questions we have? Two more. Okay. We want to find the surface integral where surface is the cylinder and the top is from and the height is from 0 to 2. You have to include, and you have to also include the circular top and the bottom. Field is given to this. Okay, let's just get the ideas at least, and we can do these things. And since we want to find the surface integral, I would rather go by divergence theorem, and I will try to compute the divergence. That will be easy. Is it okay?
Okay.
So what we want to compute is this. Sorry, why am I making this? F dot. I want to compute actually this, but by divergence theorem, I will simply write divergence of F times dV over certain region E. Of course, E has to be a solid region enclosed by the cylinder. We want to enclose that region. From radius 0 to up to height 2, we have to write all these cylinders, and we got a region which I'm calling to be E. So what is divergence F? Quickly. Del by del x plus y z plus 2 by q by 3 minus sin x z plus del by del z z minus x minus y. Yeah, but that would be is x square plus y square. Is that okay?
Yeah.
We got the divergence, and then we have to just look at the region. That's all. If we can figure out what is the region, I think we'll be done. So x square plus y square plus 1 times dv, and then over the region. Region is you have to look at the cylinder, and then it's I mean, basically you are just, how do I say? You are, if you try to look at your cylinder, z equal to 0, it's like a projection. If you take z equal to 1, z equal to 2, how would I say, how would I tell you that?
Well, Z is going from 0 to 2.
Yeah, z is somehow fixed to you. Yeah, z limit is given to me. It's 0, z from 0 to 2. And rest is the cylinder. You have to parameterize the cylinder. Yeah.
Yeah. After solving the Z part, we change to polar.
Correct. So let's just write this part: x square plus y square plus 1, then dz dx dy. Z
We get
is
2
from
as a
0.
constant outside.
Correct. Let me just write that. This is over the cylinder. Okay. I mean, what is the meaning is that you have this kind of cylinder from 0 to 2. This height is 2. I think I'm not drawing it perfectly, but this is how it looks like. You have to start from you all the time you have this radius is 1, so you are all the time packing up radius 1 tiles over it, and you are making a cylinder like this, and then the height is 2, and each time circle is x square plus y square equal to 1. Yeah, I think figure is quite natural. Yeah, now you can change to polar by writing x equal to cos theta, y equal to sin theta, and theta is from 0 to 2 pi. And your radius is also, I mean, sorry, x is r cos theta, y is r sin theta, and r is from 0 to 1. Is that okay?
Yeah.
So let's just do it. It's a simple thing, we can do it. So we got x square plus y square plus 1 dx dy over that region, whatever we have just discussed. So it will become 1 plus r square. That's all, because x is r cos theta, y is r sin theta. I can take r square common, it becomes 1. Dx dy would change to r dr d theta. R is from 0 to 1, theta is from 0 to 2. Is that okay?
Yeah.
R square by 2 plus R4 by 2, 0 to 1, and then d theta from 0 to 2 pi. I'm bit quick. 1 by 2 plus 1 by 4. I hope I don't make a mistake. 0 to 2 pi d theta. What did would be? This will be, I guess, 3 by
3 by
4.
4.
Did I do certain mistake? I think.
Mm.
Oh, that is the radius.
Radius from 0 to 1.
Okay, we missed this 2, right? We missed there is a 2 outside. Yeah, we missed this. Yeah, now it's okay. 2 times the inner part becomes 3 by 4. Then 0 to 2 pi theta, and this will be 3 by 2 times 2 pi 3 pi. This is okay, right?
Yeah.
So we got the surface integral very easily by applying the divergence theorem, by going to the divergence of f and finding the volume. Okay, let's just do this last question and then we will conclude the session. We have to find again the surface integral of a vector field over the sphere of radius a. Region is a sphere. If I ask you what is the boundary of a sphere,
It boundary.
if you project it to certain plane, what do you get?
We got a circle.
Yeah, it's a circle of radius a. Okay, so yeah, we want to compute f dot n ds. What would you do? You would do the direct surface integral, or what you would do something else which can help to compute this integration simply by certain
And
result?
divergence.
Yeah, so I will use by Gauss divergence theorem. It will be divergence of f times dv over the region E. E is nothing but the region bounded by the sphere of radius E. E is the region of the sphere of radius A. What is divergence of f?
Answer is 3.
Answer is 3. Okay, let me just check del by del x of x. Yeah, it is 3. Del by del y of y plus del by del z of z. This is 3. Yeah, you are right. So, therefore, my double integration f dot n ds would simply be 3 times the volume. Can you tell me what is this? I think you should be able to tell me.
This is the volume of the sphere.
What is the volume of the sphere?
4 by 3 pi r cube.
Mm-hmm. I should write volume of the sphere of radius a. Suppose radius is given to you. What do you say now? This is nothing but 4 by 3 pi
A cube.
a cube. Very well. So therefore, what is the integration f dot n ds? So 3 times 4 by 3 pi a cube, which is 4 pi a cube. So we got what we got is nothing but the 3 times the volume of the sphere. So the surface integral of this vector field is nothing but 3 times the volume of the sphere. Yeah, so I think we are done with the questions. Let's just go back where we left. I think that you only told me that this is done. So nothing is left then, huh? We covered everything. Okay, so do you have anything to ask or any comments to or any suggestions to make?
No.
Sorry?
No.
No, okay. And how was overall experience for learning this course?
It was good.
Okay. So did you learn something, in which can you tell me certain points which, I mean, certain topics which you liked a lot or you learned about a lot?
The topics were equally interesting.
Mm-hmm.
But like towards the last 2 weeks, we can get a bit confused regarding the formulae.
Yeah, I understand. I mean, there were several things: line integral, surface integral, volume integral, and then something with the work done, something just integral over certain curve or certain surface. Yeah, I mean, certain things were, I mean, you need to be bit careful and you have to revise and you have to be practicing many things. Then only mm, all the things will come to you together. Otherwise, there are pieces, but you might not be able to differentiate one with the other.
Yeah.
Right. I mean, there are a lot of things we covered in this 8 week of course. I think one needs to give some time to practice on all these topics. I mean, they all are, as you said, they are all not just interesting, but they are very important. And
But
I,
yeah,
I
that's
mean,
the dilemma about college life, that we have multiple subjects. So it is
mhm.
not always possible to delve deep into one particular thing.
True, I agree, but I feel like those which are more interesting to you, to anybody, and as and also you can feel that you can feel those subjects and you can also do good in that, then you should give some more time so that you get excel in those things. Of course, nobody can get excel in everywhere, everything, but we can try getting best in at least certain parts of that. So I would still recommend that. I mean, many things you can just, I should not say this, but if you can just get pass out of that and then you can spend some more time in getting, you know, doing excellent thing in one part, most of the parts, I should not say one part, then you should do that. This is what my feeling is. And it's just not about this course. Maybe you are getting interested in certain other things and you might not be able to feel certain subjects, but you can just simply, for the sake of marks, you can just pass them with fine, with some effort. But at least you should give some more time to those who, where you can feel more, where you can understand more, you can do more. That's
Well, I
all.
can
Yeah.
I can ask our director, ma'am. She's also a professor of maths. Like, okay,
Okay.
these are